I can read it to you. I started to write it on the whiteboard and it's like, oh, that's a lot of writing.
There.
So make sure you put your name on your paper.
I've started recording.
Okay, good.
You can still
So question 1 is, what gas did Nile Red use to keep the substance from reacting during the filtration process?
I left my homework home at home. I'm actually going to caution.
Yeah.
So the options are fluorine, argon, nitrogen oxide, and sulfate. Second question is, name pieces of glassware that Nile Red used that we don't have in class. So one of the things I wanted you to see was glassware that is too expensive, and this reaction, was sensitive and toxic, and even the highly graduate postdoctoral chemists had a hard time doing it. But I wanted you to see the glassware, because if you do college chemistry, you will get to use at least some of those things. I don't know at what level you use. Third question is, what bond disassociates with water? A, ionic, B, covalent, C, hydrogen. So you were to read about the ionic bonds and covalent bonds, which we'll be going over in a lot of detail. But which one disassociates in water for question 3?
So do we write down the answers or are we
Yeah, write down the answers. I'm not going to remember. Write the word down.
Do we write down the questions too?
No, you can just write 1, 2, 3, and 4.
What's question 3? I can't see it.
3 is, which bond disassociates in water? I can take it over those. I can only focus the top or the bottom.
The bottom.
So which bond disassociates in water? Ionic,
is it?
covalent, or hydrogen?
Oh, okay.
I can't see. When you're done, make sure you turn your paper in. Your pop quiz is there. Your sign quiz, which chapter up there. And anything you haven't turned in that you're supposed to turn in before. Oh, it was the same 16 and 17 from last week. So the only new assignment was to watch that video. Where is that? This is the third pile, fourth pile.
Okay. I'm so.
This is your pile. This is mine. Tall Bennett. Leah, can you keep handing out papers? So Grayson, this is your test. That's your exam. Leah's exam. That was 3. And
What's the fourth question?
the fourth question is, which bond forms between 2 nonmetals? Is it ionic, covalent, or hydrogen? What bond forms between 2 nonmetals? Ionic, covalent, hydrogen.
Daddy?
That was like too much paper. Where's Leah sitting? I think that's yours, Sam, but I put a question up there. Do you have a name?
Yeah.
Leah, do you want to keep your test packet? I still have yours.
Is this yours?
Julian.
Oh my gosh. Oh, this is. Okay.
So
I was
Grayson,
like, I did not.
here's your answer key, Grayson, and here is your exam. So, alright, so is everyone done?
Did you give us that pop quiz?
No, I didn't give it to you. I told you it would be there. So I said, I think, going forward, so you have the answer key. So you have the answer key for your test. Like we could say, everyone on your honor, don't look at the answers and study the tests, but I don't think that's realistic. So what I'm going to do is, I still want to see you turn your stuff in, and I think it's probably not a bad thing that you have the answers to see what's wrong. I'm going to give you 3 to 5 questions from the worksheets that you do as a pop quiz at the beginning of class. So I'm still going to turn your worksheets in. I'm still going to give you credit for doing them, but you're going to see something from your worksheets in a pop quiz like this. It's going to be as weird as this because I don't want to print out like 20 pieces. So it's going to look like this, and this will be just make sure you're still like doing it and not just copying and show the book. So for your exam, you have the exam and you have the answers. I'm going to change it slightly. I'm going to rewrite the exam to change something from like chlorine to bromine. I do essentially the same questions, slightly changed. So if you have the concept, you'll get it's asking you for the electron configuration. It'll just be slightly different than what you have. I think everyone except my kids should have. And then that's quizzes right here. With your name on it, make sure your name's on it.
How do you spell it?
Oh yes, absolutely not.
Alright, so like I made reference to moonshine in the email. So in alcohol production, you ferment a grain of any type, be it potato or wheat or hops or rye, and then you have to separate.
Sorry, I'm trying to figure out the questions. I couldn't
Okay,
read it.
okay, you're good, go. And then you have to separate the alcohol from, actually I'm done, but whatever the leftovers. So that process is called distillation. So in this picture here, it has a round bottom flask with a ring stand. I hope to be able to, not knowing how things are going to play out, like I'm hoping that we can add some things on the end, but we'll actually use a ring stand and have fire underneath and put some stuff. So this is a round bottom flask. That was one right answer.
Yeah, honey, got here.
All kinds of different ways.
Better not be hydrated.
Alright, so here, the chemical, the gas that he used while doing the
Though I
filtration.
also added a small tube, which would shoot in argon gas and protect everything from air and moisture.
Anyone can speculate why he used argon? Because it's an inert gas. It's a noble gas, also historically called an inert gas. So I can't help but call it that. But that's, oh well. It's common in vocational people communicating. So it's an inert gas, and it's going to keep the oxygen away. It's going to keep anything else that might react with it. An argon is in a laboratory setting when they're doing spectrometry. They'll often run argon in it to keep it. The last thing I wanted you to see. So here's a filtration setup. So this is a vacuum pump, which you're only going to have in a college setup, but Chemistry 101 would have. You'll have vacuum pumps. Well, you'll have this filtration, and it'll suck it, and it'll run a vacuum on it, and it'll dry your sample. So a separatory column. This is something that has a stopcock at the bottom. You could just think of your.
I then threw the sugar around just
You
like
ever
before
make
and
gravy?
waited for the layers to separate, and I drained each washing into a beaker. When I was eventually done, this was what I had.
So that is like the laboratory equivalent of a gravy fat meat juice separator. Like when you pour off the bottom, you make gravy. The last thing I want to go digging for, because I want to move forward, was I call it a distillation column. He actually called it a condenser column. And it is something that, this is what I'm going to try and review, is that's what those loops would do, is it evaporates off, and any moisture that's in it will flow back into your flask, and your alcohol or any more volatile substance would then be collected at the end of your collection. Alright, cool. So what two metals make a covalent bond? Whoops. What do non-metals make?
Covalent bond.
Covalent bond. What was the last one? What type of bond associates in one?
Ionic.
Ionic.
So, this one is
Let's see. Don't forget. And so we are going to talk about two chapters today. Because originally I was trying to condense it, so I made sure we do the most important things that you were complete. I just don't know the future of our time here. So, I'm kind of wavering between moving fast, but then maybe we'll add stuff on at the end, or I don't know. So we're going to wing it. We're here today. We're going to do an exam next week, and the basis of our last formal lab report. So we're going to talk about both ionic and covalent bonds. Oh yeah, it's right here up in my class. So ionic bonds.
Holy, like the really
And
close.
so they are an attraction between a positive and negative. So we're going to start talking about batteries. You can think about magnets, positive and negative charge. The positive one is say it for me please. Cation. The negative one is besides Lucas,
Anion.
an anion. Can you say it together? Positive is
Cation.
not anion.
Cation.
Cation. The negative is
Anion.
anion. Alright, so this is an intramolecular force. So we're going to talk about inter within a group and intra. So intra means it's attraction between the outside of the molecule. So it is not within the molecule, it's outside of the molecule, two opposite forces. So some examples are sodium chloride, I'm not going to say, are these. Now in class, it was not in your book, we learned about how to name an ionic salt. We gave the cation the name of the element, and we changed the anion, the ending of it, to be an IDE. So can you guys write down, figure out, think about it. What would you name these three molecules? Cation gets its elemental name. Second one, anion gets the IDE ending. Alright, so the first one,
I can't see the third one.
it's Al, aluminum, and F, fluorine. AlF3. All right, can you name them? First one. What's the first one? Sodium chloride. Second one with magnesium and bromine is
Magnesium bromide.
magnesium bromide. Third one with aluminum and fluorine.
Aluminum chloride.
Aluminum fluoride. Yeah, that's so good. All right, so an ionic bond is an intramolecular bond. An intermolecular bond that works in the same concept is a polar molecule. A polar molecule has both a positive and negative, just like our ionic bond. And the electrons are drawn more to the more electronegative side of the molecule than the other. So we have these little squiggly lines, they're called deltas, and they represent a partial positive and a partial negative. Because oxygen is more electronegative than hydrogen or just about anything else, it will pull the electrons to it, giving it a partial negative charge, which is represented by those deltas, and the hydrogens will have a partial positive. It's the same principle as that ionic positive and negative attraction we're going to see within this molecule, but then they're going to be attracted to each other, and a word that you'll get tired of hearing in the future, the dipole-dipole force, or dipole-dipole attraction. Say dipole-dipole. So like I had it, one of my the least favorite chemistry professors was Indian, and he had a very sing-songy accent. So he'd go dipole dipole, dipole dipole. I can still hear that echo in my brain. So say dipole dipole. That's like a trauma phrase for me. So the dipole dipole attraction is between the negative end of one molecule to the positive end of another. And this is the intermolecular force. So if you look at your periodic table, if you want to break it out. So electronegativity tends to increase this way. So molecular size increases as you go down, and electronegativity increases as you go across. So these atoms here will be most electronegative, decreasing as you go this way and this way. So as we see up here, where oxygen is, this is why we tend to have a high degree of electronegativity, because it's both negative and small. So when you're trying to look at a molecule and figure out which side is positive and negative, or is it nothing, you can think about where it lands on the periodic table. So, as we've been trying to find out the charges of our anions, we see these tend to be positive. These will lose one electron and become +1. These will lose 2 and become +2. On the opposite side, these will lose 1 and become -1, -2. But we get to this group here, and it gets a little funky. It can kind of identify it doesn't, it's capable, but it isn't stable. So this is the group 3A. So we see up until carbon, it goes -4. Now up until beryllium, it goes +2. So let's look at boron, if you can find boron on your periodic table. So boron's electron configuration, actually I had to correct this one because I was wrong later, because I copied and pasted too much and didn't check it. So you can double check me. This is just copied and pasted from previous ones, so I make lots of mistakes. Then you want your periodic table, or Sam's got one. Alright, so if we look at boron, group 3A, it's going to have the electron configuration. It's in the second row, so that principal quantum number, or outer shell, is going to be a 2, and S1, S2, as lithium and beryllium, and then we go over to boron, and we get our first p orbital. So 2p1 is the last orbital that is filled. All right, so it has a choice. It can either lose this last electron and have its s orbitals full in the second shell, and that's something, but it's still if 2 is incomplete, but that orbital is, so it's something. It's not bad. It could live like that, but it doesn't really want to. Or it could lose 3 electrons, which is a lot to give up, but then its first shell, only shell, is full. So it has kind of those two options. It tends to live where it's only one s2, making it, losing it 3 electrons, being +2. But it is capable of doing both for a short amount of time. So it exists. All right, aluminum should be the next one below. So what is the principal quantum number of aluminum by counting the rows down? Someone show me fingers if you're not going to speak. 3. So it gets down to, just like beryllium, it has 1 in a p orbital. So it can drop that 1 and have 2 in the s orbital. Or it can use 3 and give it a plus neutron, which is more stable. So, not in your book, but from last week, we talked about oxidation states by switching the charges to see how the molecule would form. So I'll do this first one. So we have B2O3. My question to you is, what's the oxidation state of them before they react? So if they were separate, what was the plus and minus? So I would take the 3 and put it over here, and the 2 and put it over here. Remember how, I guess this was 2 weeks ago, that we crossed them. So that would tell me boron had an oxidation state of 3 something, and oxygen had an oxidation state of 2 something. I don't know which one's positive or negative, but when looking at our electronegativity, where they are on the periodic table, I'm going to understand that 2 is negative and 3 is positive. In reality, these are often usually represented as Roman numerals. So positive, negative. So that's how I would figure out what the oxidation state was. Which one is the iodine, which one's the cation, from the chemical formula. So I have to know where they're located, and I switch them. So I'm going to have you do the next one. All right, the oxidation state of each atom in aluminum chloride. AlCl3. Switch my subscripts. And I have to figure out which one's going to be negative and which one's going to be positive.
Chloride is negative and the other one's positive.
So when you are in the transition metals in particular, sometimes like copper can exist in many oxidation states. Iron can exist in many oxidation states. All right, this next one's a trick question. I'll just tell you right now. Let's see if you can figure out. Carbon dioxide. What's the oxidation state?
Okay, one.
But that's wrong.
Alright.
Oxygen doesn't like to be 1. But if I multiply both of those by 2, carbon becomes 4, and oxygen stays 2. That's what it actually is. I multiplied. Which one's positive and which one's negative?
Carbon's positive, oxygen's negative.
This one's not a trick question. Methane, CH4, basic 4. All right, what's the charge of the oxidation state of carbon going to be?
It's gonna be -4.
And hydrogen?
Positive
Hydrogen
1.
always likes to be
+1.
positive 1. I'm going to reiterate this because I think I misspoke because grammar, words, inflection is not so good. The first one, the ionic bonds, they have intermolecular bonds. They're called intra. It's within itself. Which one means within itself? Polar has between molecules. I'll make sure I got that prefix right. So ionic bonds are within the molecule itself. Inter means within itself. Intra means between with it and another. Which one is intra? I-N-T-R-A. The polar ones. The polar bonds are intra between them and that molecule and another molecule. A ionic bond is inter between its anion and cation. Do you guys have any questions about ionic bonds before we move on? Does it disassociate in water? Yes or no?
Yes.
Yes. All right. Are salts ionic or covalent?
Ionic.
Ionic. All right. So covalent bonds are different. They are between two or more non-metals. So it is an actual physical link as opposed to a charge attraction that we saw in ionic and polar bonds. The electrons are shared between the outermost shell, or the valence electron. So oxygen has 1 filled, 2s filled, 2p partially filled. It still has space for 2 more electrons because the Y and the Z only have 1 electron each. It would be happiest if that shell is full with 2 more electrons in it. So instead of the 2 single electrons, those orbits, it's going to share it with another one. Since another oxygen, also a short 2 and has 2 spare, it will share those electrons in a covalent bond. And it would have been nice to find a graphic that showed how they actually don't stay in between. This is how we represent it, but just like our orbitals are they don't stay in their orbitals, they become hybridized. These electrons don't stay between it. It ends up being an electron cloud that just moves all within everywhere. So they satisfy the octet rule that we see for at least the top half of our periodic table. And they make 2 covalent bonds because 2 electrons are being shared. So it's stronger than an ionic bond and won't separate in water. So did you guys get introduced to the Lewis structure? I believe what my kids told me, this is interesting when I read what I expect to be there and I don't see the vacancies. I think, okay, this concept's being covered. And then I often find out, well, this wasn't covered. And I wouldn't have picked up on that unless my kids are saying, we didn't learn that. Did you learn the dashed lines representing a covalent? You did learn. Okay, some of you are better than others then. So when there is a covalent bond and 2 electrons are shared, it's represented as a dashed line. So if I wanted to see if the octet rule was being satisfied, I count 1, 2, 3, 4, 5, 6, 7, 8. Each of these oxygen claims ownership of all 4 of those electrons represented by the dashed lines. Alright, so nitrogen also is a nonmetal, it covalently bonds. Should have actually figured this out, but its electron configuration looks like a full first shell and a partially full second shell with 1 electron vacancy in both the X, Y, and Z orbitals, p orbitals. So short, 3 electrons, but also 3 electrons available in that p orbital to share. So instead of making two covalent bonds like oxygen, it will make 3 covalent bonds. Do you want to try and write the Lewis structure for nitrogen? Just give that a try before I show you the answer. Try and write the Lewis structure, knowing that it has, in its principal quantum number, outermost shell, it has 2 in the S, and then 1, 2, 3 in the P. And it'll make a covalent bond with another identical nitrogen. So 2 nitrogens, what do you think that would look like?
Oh,
It is short,
it did
3
share.
electrons to make, to satisfy the octet rule. So it needs 3 more. So how many covalent bonds do you think it'll make? So it'll share 6 electrons and add on 2 more to get to 8. So polar molecules with that charged side, partial positive, partial negative, will have covalent bonds in it. So we've got ionic bonds that are charged, and then we have polar molecules that have covalent bonds. Can you like at least smile? This looks so, thank you, Maddie. So it has a covalently bonded electron. Now that's a grimace, not a smile. So with a partial negative on our more electronegative end and a partial positive on our 2 positive. Those means the positive and negative areas don't balance. That's kind of interesting. It's not 1 for 1 because it's within the region. All right, so in non-polar covalent bonds, electrons are shared equally with no partial charge. So not all covalent bonds are polar. Would a nitrogen be polar?
No.
Would an oxygen be polar?
No.
All right, so the final type of bonding, I think they talked about this, was hydrogen bonding. I don't think they talked about it very much. What did they say about hydrogen bonding? Anything?
It said stuff.
Stuff. Certain things. All right, so again, that's my favorite word. Like, what's this word? Type your word. It's like a brain. Double.
Dipple.
Say it. Dipple. The dipole. The dipole attraction. So it is again present here in hydrogen bonding, just like it was in ionic bonding. There's a positive end and a negative end of our polar molecules. That hydrogen is so, don't want it, I'm positive. It tends to be a polar molecule because it's so not electronegative. So due to the hydrogen being covalently bonded to any electronegative atom, like look, where are these oxygen, chlorine, and nitrogen listed? Where do they end up on your periodic table? Like, put your fingers on one hand on them. Are they on the top right of your periodic table? Yeah, in in that area of electronegativity where they're both negative and small. So they cause a unique crystalline formation. So all these will be, beginning with a hydrogen bond, will tend to form a crystalline structure. So, like ice floats because it's crystalline. Most things, when it gets cold, it gets denser, and then it sinks. And cold water does sink, but then once it reaches a certain freezing point and it achieves that crystalline structure, it comes up, and it's the reason life can exist, because it's has that unique property, or otherwise things would freeze and they just fill up and lakes would be solid ice and fish would die and all that stuff. So, it's kind of important. So hydrogen is attracted to the nitrogen of N3, NH3, ammonia. So ammonia will have a positive nitrogen end, a negative nitrogen end, which will then be attracted to the positive hydrogen of the next ammonia atom, creating a crystalline structure, or tendency. Alright, so next week we are going to start with our exam, and then we are going to move into our most intensive lab. We're going to have 2 parts of our lab, both of them only looking at ionic structures, because covalent bonds aren't that interesting. They just don't do much. I encourage you to read through the lab that talks about covalent bonds, but there isn't much to see. So we are going to look at ionic bonds. We're going to have 3 solutions. So I do want you to read through the lab in your book, but we're also going to have a second one that is in addition to that. So it will be a 2-part lab. So this will be your final formal lab of the year. So I'm going to expect the most out of it. I want a well-developed introduction where any sort of scientific term that you discuss later on, ionic polarity, partial charges, electronegativity, that you identify and define those in the introduction. Your procedure is bullet listed, or your materials are bullet listed, your procedures are concise. You need to use graphs. Grace, I think you missed our graph lesson too. So I want to revisit that, and we're going to have 2 or 3 weeks so I can help you get that equation fitted to your graph. So you're going to make the scatter plot, fit your trend line, add your equation, and that R squared will tell you if it's statistically significant. You can make graphs that say anything. This is even as a layperson, someone says, oh, we see this correlation in something, we have this graph, we have this trend. If it isn't statistically significant, if I ask you guys, how many of you like pizza, and then I all of a sudden say, all homeschoolers like pizza, that's just, you're a small sample size, I can say anything I want. Statisticians can produce a lot of bad data. But this is also how predictive AI and a lot of the technology that is becoming emergent that you're going to have to be prepared for, this is how these things are generated. So knowing how models work and how they don't work and how they can be used and how you can use them yourself is really useful and important. So we're going to start with 3 sodium solutions. Sodium chloride, drawing on it. We're going to use multimeters to measure the resistance. How many of you use voltmeters? Sam, I'm looking at you. And they're not called voltmeters, but I can't stop saying that term. Multimeters, you're going to look at the resistance, the ohms. Maybe we'll talk more about electricity and how Ohm's law and how conductivity and resistance works. Current that's carried through. Maybe we won't. I don't know. But we're going to plot a relationship between the concentration of the sodium chloride and the resistance. I don't honestly know what it's going to be. I don't know if it's going to be 1-to-1. I don't know if it's going to be logarithmic. I don't know if you're going to come up with the same answer. But you're going to tell me if it's statistically significant by your R squared. And then we're going to use the second part. Both parts of these will be in the same lab report. The same introduction, you probably have different material lists, call it part A and part B, but both of them are covering ionic bonds. We're going to talk about the concentration of different sports drinks, Gatorade, someone made me buy coconut water yesterday, sodium chloride solution and orange juice. And we're going to see what actually makes, I know, I'm totally downing the Gatorade. Like we did the artificial colors earlier for that chromatography thing. This is totally my bias. There's no one exists without a bias. I'm anti-Gatorade. So we'll see if it actually has more electrolyte content than coconut water or like, you just probably drink big streams of salt water that are all and we'll use distilled water. So I don't know how you're going to present that data. That'll be interesting to see because that's not a correlation.
You're doing great, sweetie.
That's it. So just a refresher, since I think about 70% of the class did the graphing project. About 30% did not. I know it was hard. A lot of people were close. So just to reiterate, try and focus it. If you are in Excel, and I did learn you were perfectly capable of doing this in Google Sheets because that actually turned out really well. You start by making a graph of your control or your independent variable against your dependent variable. You'll pick your graph. I want you to pick scatter plot. Once you get it, you can either add a trend line earlier on or add it at this point. You will click Add Axis Titles, Chart Title, Legend, I like a legend, and then trend lines you can adjust how, like this one does go 0 to 6, but I could have had it start lower if all my data was skewed. I will add the trend line here, right clicking on my data set, add trend line, and then when I go to edit the trend line, I will make sure to add down here the R squared and the equation, so they're displayed on the graph. So the final product will look like some generated equation and an R squared value. And you'll click through the different types of equations, logarithmic, exponential, polynomial, to find the highest R squared value, and that'll tell you it's the best fit. And if you recall, R squared was generated by measuring the difference between the line that it generates and each of those data points to find the best fit.
Oh, sorry.
All right, that's it.
Okay.